Good morning. My name is Balwinder. I'm going to talk about implications of quantum computing platforms for software engineering practice. Some credits before we start. I have taken help from some online resources while preparing these deck of slides. So the questions that we have explored are looking at important characteristics of quantum computing platforms. Those characteristics which are important from the perspective of business software development and how those characteristics impact the architecture of quantum software solutions and how how building a quantum software solution is different from the conventional software development, the software for conventional computing platforms. So these are the things that we wanted to explore, and the reason we are looking at quantum computing is because of its enormous potential. There are applications where the quantum technology can outperform the classical computing platforms by orders of magnitude, and the applications range from cybersecurity to sensors. We are talking of quantum AI and so on, and various areas such as drug discovery, financial modeling, weather forecasting, etc. They are all important areas where a lot of effort is being spent in exploring quantum applications. However, the field is still in its infancy, though quickly evolving. So there are opportunities for early adopters, people who are able to gain some critical insights early on will likely lead in that space. And as a programmer, it's important because programming a quantum computer is different from how we are used to programming our classical computers. And major players in this field are Microsoft, IBM, Google, D-Wave, Rigidity, and there are many others, of course, but these are the major players as of today. Now, before we explore the questions that we highlighted, these questions, before we explore these questions, let's look at a broader context of software development. So, a software application typically is built for or on using some computing platform. For example, using cloud platforms or for deployment on an IoT setup. And today we are talking of quantum computing. So always there will be a target computing platform. And the application, apart from its functionality, has to ensure certain levels of quality attributes in it. Quality attributes such as the availability, reliability, manageability, and all those star abilities that we usually talk about. And these QAs, quality attributes, are realized using various design tactics, and those tactics exploit or mitigate certain platform-specific characteristics. For example, if you want to improve the performance, let's say, of an application, so one of the key things is try to exploit parallelism. So if my platform does not have capabilities of, let's say, multi-core CPUs available, and I'm talking of a classical platform, then realizing that parallelism potential becomes a little bit difficult. So if you have parallel CPUs and cores available, then certain parallelism may be exploited. Parallelism that is present in your problem may be exploited there. So likewise, there may be other characteristics of the platform which may have to be mitigated in order to ensure certain level of quality attributes. So basically what we are saying is that these characteristics play an important role in designing the application so that certain level of quality attributes can be achieved. Now, once we have this understanding, we will be now moving on to looking at specific characteristics of quantum computing platforms. Now, before we do that, let's quickly contrast how the classical computers and the quantum counterparts differ in certain areas. So information is represented using classical bits on a classical computers, bits 0 or 1, which could be realized by some physical properties of certain physical devices, let's say. And whereas on the quantum side, we call them qubits, and they also in a similar fashion are realized using suitable physical phenomena that obey quantum mechanics laws. Now, on a classical side, at one time, if you take n bits together, you can represent 2 power n distinct states. Whereas in the quantum case, you have a qubit and you have basis states represented as this 1 using bracket notation and this 0 using bracket notation, and the states could be superimposed. These basis states could be superimposed in some kind of a linear fashion. So each of these basis states are actually vectors, and the superimposed basis states can represent a very large state space, because these quantum qubits, when they are superimposed, they can be at the same time, at any given time, can be in all the possible combinations of this superimposed state as it is expressed. So that is what leads to the exponential increase in the state space that can be represented using the same 2 qubits when they are superimposed. However, the observation of these qubits ultimately collapses them into the basis states. In other words, when you observe these qubits, they will only be observable in one of the basis states, even though they may exist in a superimposed state. So these are some important characteristics. In addition to that, another important characteristic of quantum qubit is that it can be entangled with another qubit. So what it means is that when 2 qubits are entangled, that means individually when they are observed, they may behave randomly, they may be observed as random. However, together they will be strongly correlated, right? So, for example, if you hold a qubit which is initialized, let's say, to value x, and I hold another qubit which is entangled with the one that you hold, when I observe that state of my qubit, it may appear to be having some random value based on how I have initialized it, of course. And similarly, when you observe your qubit, it will also appear to be random. Now, but whatever you observe, the same value will be observed in my qubit. So that's how the two are actually correlated when seen together, but individually they are random. So that is an important property which is exploited in many quantum computing algorithms. And so just to summarize, these are some counterintuitive ideas of quantum physics which play out when we are looking at quantum computing. So moving on, when we build a quantum software, how is the system's structure looking like? So typical architecture of a QCP based application might look like this. So you will have certain layers which are composed of purely quantum machinery, quantum devices, and certain part has the classical layers. Classical are implemented using classical computers. So the basic devices consist of something that realizes my qubits using suitable technology. Somebody may use, let's say, superconducting loops. And then you have, switching and addressing mechanism, all at the quantum hardware level. And then you will have quantum logic gates realized. And then there will be a quantum classical interface. And then on the other side, you will have quantum programming environment, which should give suitable abstractions to represent a quantum device, quantum state, quantum logic gates, and ultimately quantum algorithms expressed as suitable sequence of application of quantum logic gates. and there will be necessary tools for simulator support and circuit composition, etc. And this is what is going to be my quantum programming environment. And then in some business application, I will be, invoking this quantum circuit, which ultimately will be generating some suitable instructions which are passed down to the quantum layers. So broadly, this is how the architecture of a typical application might look like. And in other sense, the programming model will require you to first decide what is the encoding between bits and qubits, because the information that you want to process using a quantum application still has to come via the classical computers. So there has to be some mapping defined, some encoding defined when you take data from bits to qubits and vice versa. So you decide that, and then there has to be suitable setting up of the state, the qubit states, and then you apply the quantum algorithm using suitable sequence of quantum gates. I'll show an example in a minute. And then after you run those algorithmic steps certain number of times, because all the quantum algorithms are probabilistic in nature, and then you measure the output and finally transfer the data back to the classical bits. So that's the typical programming model. And once you understand this and explore the details available for various quantum computing platforms which are available today in the field. For example, we explored IBM quantum experience, we explored Rigetti's APIs as they are available, and Microsoft quantum toolkit that is available, and so on, to identify certain characteristics of quantum computing platforms. They are listed here, and I'll highlight the implications for some of them in the subsequent slides. But just to go over these, enumerate, so the first thing is that the programming abstractions that are available to you for creating quantum programs, you have to work at a very low level. We are working at quantum logic gates level and composing quantum circuits. And then platforms, there is a heterogeneity there, and there is a very specialized physical environment involved. And similarly, the form factor is very large. The quantum computer is physically quite large. And there are studies of energy efficiency that has been reported in literature. And it is reported that the quantum computers, for a given compute capability, they are more energy efficient than the classical counterparts. And the development of software takes a remote model of development. Means you access the quantum computing facility remotely via cloud, as is the example with, let's say, IBM quantum experience. And this is important, dependency on quantum algorithms availability. If you do not have suitable quantum algorithm to which you can map your problem that you're trying to solve using quantum computers, then you won't be able to use those platforms. So this is then remaining set of characteristics which are identified. Now, when we move forward, here is, let's take one example, the lower level of programming abstraction I mentioned. So you are working at the level of, this is an example taken from IBM Quantum Experience. This is a screenshot of the circuit composer there. So you use some visual tool to compose your quantum circuit, which makes use or which works on these 5 qubits, right, which are initialized to some state, and you apply certain quantum gates. H is Hadamard gate, and then subsequent gates are used, and finally the measurements are done on certain qubits. And of course, you have a programming interface as well, where you use a Python-based API that they expose for similar operations. But the idea I'm trying to expose here is that when you express your algorithm, you have to work at a much lower level than what we are used to doing in our classical programming. So that has implications for, obviously, maintainability of the code, and how much you can express is also limited by the number of gates, etc., that are available and the operations that you can do, right? So in that sense, this is a very low level of abstraction that one has to deal with. Then dependency on quantum algorithms. So if you want to make use of a quantum computer, the problem that you, as I said, want to solve should be mappable to a known algorithms. Unless you develop a new algorithm for your problem, you have to work with whatever is known today. And today there are only a handful of algorithms available. So that itself is a limiting factor. Now these are some of the properties which are exploited when building the quantum software, when building the quantum algorithms. So amplitude amplification is one property which is typically exploited. Example is Grover's algorithm, which is a search algorithm. Similarly, quantum Fourier transform is a technique. Phase kickback, quantum phase estimation, quantum walks, they all have found applications in certain specific algorithms. What I want to convey is that these techniques, even though I have listed only 5 of them, there may be a couple of more, so they are limited. Hence, your ability to devise newer algorithms is dependent on how many such techniques you are able to identify and are known to you. So that, in a way, becomes a limiting factor. So when you design your solution, when you build your solution, you ultimately depend on the workings and knowledge of these techniques. So portability is limited because each of these providers offer their proprietary APIs. So in that sense, if you work with Cirq, and then open QSM, they may not be interoperable. So that leads to some implications for the engineering aspect of your software. Now, after having identified these characteristics, we explored the implications for various quality attributes, and these are our findings, and we have listed it in our manuscript, which is available on archive as well. For example, the specialized physical environment. A quantum computer requires a very specialized physical environment. So availability is unfavorably affected. And similarly, manageability is unfavorably affected, and so on. So likewise, by analyzing these properties and what is the definition of each one of these quality attributes, how they are realized, we did that analysis and figured out how they might impact each one of those. And similarly, for software development lifecycle activities such as your requirements phase, your design, construction, testing, deployment, and through to maintenance, whether they are affected or somehow we are not able to find the effect or neutral, that has been analyzed. For example, if you look at low level of programming abstraction, so requirements generally is unaffected, we have seen. Whereas the design is almost always affected by all of these, as we have seen briefly. Because, for example, construction, if you take, that is affected, and similarly testing gets affected by various properties of the quantum computing platforms. So in general, there is a significant implication when you design your solution using quantum computing platforms. So revisiting our questions that we started with, we looked at various characteristics of the quantum computing platforms from various perspectives, and about a dozen have been identified, and then almost all the quality attributes are impacted by these characteristics in one way or the other. And obviously building the software on a quantum computing platform is different from how we have been doing for a conventional platform. One thing I want to note is that basic design principles don't change. They still remain applicable. However, the characteristics that we have identified, they lead to implications for effect on quality attributes, and the SDLC tasks. So concluding the talk, basically what we have found is that the quantum computing platforms are highly specialized in nature, and as such the use for general purpose business applications, at least as of today, is limited. Many reasons for it. First thing is the algorithms itself are very specialized. Whatever is known today is highly specialized. Not all business problems may be mappable to those algorithms. And then the design or the availability itself of the practical quantum computing platforms is a factor. So in future, probably the co-design of quantum classical hardware software systems may be a useful direction to explore. Technology diversity is going to stay in the software solution. Technology diversity in the sense that you have to both consider classical as well as quantum platforms when you're building solutions which exploit your quantum capabilities. So these are some of the references that I have cited in some of these slides. Thank you. Finally, thank you for your attention.